What's up, everybody? In this video, 2020 February contest at the silver level, problem 1, Swapity, Swapity, Swap. Farmer John's N cows, where N is between 1 and 10 to the 5th, are standing in a line. The I-th cow from the left has a label I for each 1 less than equal to N, I less than equal to N. So basically, all the cows are standing in a line 1, 2, 3, 4, 5, and they're all labeled with the numbers of where their position is. So all the cow number. Farmer John has come up with a new morning exercise routine for the cows. He's given the cows M pairs of integers, where those pairs are L1R1 and then L2R2 up to LMRM, where M is between 1 and 100, so up to 100 pairs of integers. He then tells the cows to repeat the following M-step process exactly K times, where K is between 1 and 10 to the 9th. The 10 to the 9th is a big red flag. You're not doing anything 10 to the 9th time and getting it done with the time complexity. So this is going to require some sort of division or modulus math. Anytime you see a number that large, you know you're not going to do anything that many times, because it just, even a for loop that goes from 1 to 10 to the 9th is going to time out. For each I from 1 to M, the sequence of cows currently in positions Li up through Ri from the left reverse their order. Right, so for example, L1, R1 would be represented as two numbers, for example, 2, 4, and that would mean that the cows in positions 2, 3, and 4 would reverse their order. So then they would become 4, 3, 2 instead of 2, 3, 4. After the cows have repeated this process exactly K times, so just to clarify, there are M swaps, and we will do all M of those swaps. And after we are done, we will do it again and again, and we will do it K times. So you have to do M swaps K times, which is M times K operations. And again, 10 to the 9th is already too big. M goes up to 100. We're definitely not going to be able to do 10 to the 9th thing, 100 things 10 to the 9th times. Please output the label of the ith on the left for each 1 less than equal I less than equal to N. So basically, once it's done, after they've done M operations K times, we want to display where they all are, where they're located. Test cases 2 is NK equals 100, 3 through 5 are less than 10 to the 3rd, and then 6 to 10. Basically, if you want to get more than half the test cases, you're going to have to do something efficient. You can brute force the first, like, maybe 5 test cases, but you have to have something optimized in order to get through the last ones. And there's several optimizations to this that you're going to have to be able to use. So let's look at the input format here. Input format comes from a file called swap.in, where the first line contains N, M, and K. Okay, so N is how many cows, M is how many swaps, and K is how many times you want to do all of the swaps. And then for each 1 less than equal to I less than equal to M, line I plus the line I plus 1 line I plus 1 line. No, that line's supposed to be there. Line I plus 1 contains Li and Ri, both integers in the range 1 through N, where Li is less than equal to R, or less than Ri, not less than equal to. So strictly less than Ri. So basically, every one of these swaps, the first number has to be smaller than the second number, and that's describing a range. So for example, let's run through this sample case here. So I start with 7 cows, numbered 1, 2, 3, 4, 5, 6, 7. There are 2 swaps. The first swap is 2 through 5. So 2 through 5, indexes 2 through 5 will reverse their order. So I'll have 1, and then 5, 4, 3, 2. And then 6, 7. The next swap is indexes 3 through 7. That's going to be 3 starting here up through 7. We're 1 indexing this, by the way. So index 3 is going to be the third thing. That'll get reversed, and I'll have 1, 5, and then 7, 6, 2, 3, 4. So after my second swap, that's what I'll have. But I need to do this process again. So once again, then I'm going to swap indexes 2 through 5, which is going to give me 1, and then 2, 6, 7, 5, 3, 4. And then I'll do the second swap again, and then I'll have 1, 2, and then 4, 3, 5, 7, 6. If you look at the sample output here, 1, 2, 4, 3, 5, 7, 6, that's our expected answer. So this is the process, and the procedure is fairly simple as far as just brute forcing it. The question, though, is how do we optimize this? There's a couple optimizations that we can use. And if you haven't had a chance to play with this, I would recommend pausing the video. Try out a couple different swaps and just see if you can figure out if there's any patterns. I would definitely go through the process of writing these numbers out, actually writing out the swaps. Maybe do this, change this K to like a 5 instead of a 2, and see if you start to notice ways that you might be able to optimize. And I'm going to switch us to a blank screen here. Let me actually write down the sample data. We have 7, oops, come here, 7, 2, 2, 2, 5, 37. That should be all we need to generate the output. Okay, so you basically got two steps to this process. Your first step is figuring out, after doing the M swaps, where does each cow end up relative to its starting position? And the reason why is because it may have occurred to you that if we know what's going to happen to each cow over the course of M swaps, we don't have to do those M swaps again. Let's write that out, and I'll kind of step through what that means. 2, 3, 4, 5, 6, 7. First swap was 2 through 5, which gave us 1, 5, 4, 3, 2, 6, 7. Second swap was 3 through 7, which is going to be these indexes here, which is going to give us 1, 5, and then 7, 6, 2, 3, and 4. Okay, so we don't really care about this middle step. I'm going to go ahead and erase it. What we really care about is where did they start and where did they end? So you see cow 1 went from 1 to 1. Now, what that means is if we were to go 100,000 more steps, cow 1 is still going to be in step 1. And the reason why is because every single, there's no randomization to this. You can't go from like 1 to 1 and then somehow miraculously go to 3, because every cow goes to exactly one location from whatever position they're in. Cow 2, whatever cow is in index 2 will always go to index 5. Whatever cow is in index 5 will always go to index 2. So what that means is that if I were to do M swaps again, I would expect cow 1 to be here. I would expect whatever is in this position to have ended up in this position, which means that the 5, which is in that position now, is going to end up there. And that's actually where it started. Likewise with the 2 is going to end up here, which means that every 2 times we do these M moves, they're going to swap and swap back. So think about the implication of that. If I were to go 100,000 steps down here, all I need to do is figure out whether this is an even number or an odd number. If it's an even number, they'll be back where they started. If it's an odd number, they'll have switched positions, which means, again, I don't need to actually swap their positions 100,000 times. I just need to know how many times am I going to do these M operations. If one step of M operations causes them to just switch position, then 2 steps is going to put them back where they are. 4 steps would put them back where they are. 1,000 steps would put them back where they are. 1,001 steps would leave them in their swapped positions. Which brings us to the next group. So we've got two examples, one where there's just a single item that stays in place, one where there's 2 items swapping positions. But let's look at the remaining numbers here. I'm going to mark off 1, 2, and 5, so we just ignore them for a second. 1, 5, and 2. Okay, so let's look at what happened with these guys. 3 ended up in position 6. 4 ended up in position 7. 6 ended up in position 4, and 7 ended up in position 3. So on the next step, we know that whatever's here is going to end up in position 6. So that's where 7 is going to go. We know that whatever's here is going to end up in the last position. So that's where 6 is going to go. The thing in position 6 ended up in position 3. So 3 is going to be, that's wrong. Hold on. 3 ended up in position 6. And then 6 ends up in position 4. I have that backwards, those arrows crossed. 3 is going to end up in position 4. And then 4, which is in the last position, is going to end up in position 3, 4. Okay, and that pattern is going to follow. Now, drawing these out this way, this is kind of hard to see what's going on. But if you look at this, the thing that's here in position 3 ends up in position 6. Whatever's in position 6 ended up in position 4. The thing in position 4 ended up in position 7. And the thing in position 7 ended up in position 3, which is where it started. So let's try to write this out a little neater, because what's happening here is we're running these through essentially a cycle. I'm going to clean all this up. We're running these through a cycle, and they're kind of like following each other in a line. And they're following each other in a line in a very predictable way. It's 1 and 5, 1, 5. I don't want to rewrite all this. 3, 4. Okay, 1, 5. What was here? 2, 2. Okay, so again, ignoring the 1, ignoring the 5, ignoring the 2. I just want to focus on these numbers right here for a minute, because this is the key to unlocking this problem. So the thing in position 3 went to position 6. The thing in position 6 went to position 4. The thing in position 4 went to position 7. The thing in position 7 went to position 3. And now we've gone in a full circle. So what that tells us is, again, very similar to the last example where we have the 5 and the 2 swapping positions. I've got these 4 following each other around kind of in a parade. The thing in 3 goes to 6. The thing in 6 is going to go to 4. The thing in 4 is going to go to 7. The thing in 7 is going to go back to 3. And that's going to be a loop. So following that loop, then what's going to happen is that's going to cycle, and that takes 4 steps to cycle. So similar to how when we had the 2 and the 5 switching position, we just needed to know if it was even. If we want to know what's going to happen after some number of steps, we don't need to do all of the steps. If I have 50 steps, for example, and I know that 4 steps takes me around in a loop, I can just divide that by 4. 1, 4, 1, 0, goes in twice, 8, 2, remainder 2, which means that everything will be 2 steps from its starting point if we go 50 steps, because every 4 steps is going to be negated. Only the leftover 2 steps are what matters. And you can do that with modulus. It'll just be 50 modulus 2 to get your remainder. So what that tells us is after 50 steps, in this example that I'm doing, the 3 is going to be in position 4, because it's going to go from 3 to 6, and then from 6 to 4. The 6 is going to be in position 7, because it's going to go from 6 to 4 and then 4 to 7. The 4 is going to go from 4 to 7 and 7 to 3, and so forth. So what we need to do ultimately is we need to build ourselves a list where each list represents a group of items. Group 1, group 2, group 3 in this case. Group 1 only contained item number 1. Group 2 contained items number 2 and number 5. And group 3 contains, in this order, 3, and then position 6, and then 4, and then 7. So what that tells us is for each of the individual cows, if we want to know where they're going to end up, we can just follow this list. Cow 1, after 1 maneuver, will end up back where he started, where she started. Then after 2 will be where she started, and where 3 should be where she started. With cow 2 is here. If there's 1 move, then it would be 1 step to go to 5. If there's 2, it's back to 2. If there's 3, it's here. If it's 4, it's there. So what you can do in order to figure out your starting point is take the number of moves, whatever it is, k, divide it by the length of this list, which is 2, and get the remainder. Whatever your remainder is, that represents essentially what index you're going to have. So for example, if it's remainder 0, then you're on index 0. You're back where you started. If you make 0 moves or 2 moves or 4 moves, you're back where you started. Same is the case with 5. If I were to take 5, I want to go, if I have a remainder of 0, I will go 0 steps from this position. If I have a remainder 1, I need to go 1 step from this position, which, the 1 step is going to loop around and then put us back at the 2. You can do any of a number of things using a for loop, or you can just use math to calculate. Math would probably be the easiest way. Whatever your starting index is, for example, in this case, 5 starting index is 1 in this list, plus your remainder when dividing k by however many things are in the list will give you how far you're stepped from your starting location. And then you'll do that modulus the length of the list again to figure out where you end up. And we'll look at that again with the 3 through 6, if that's not totally clear. With the third set here, same exact story. Whichever cow you want to know about, if I want to know about cow 3, then I'm going to start from the position where cow 3 is. Whatever my k is, I'm going to divide it by 4 in this case. So let's say like I want to do 7 moves, or I want to do 7 full cycles of that M sequence swap. I want to do that M swaps 7 total times. I would divide it by 4. I would get my remainder. My remainder in this case would be 3, which means that for each cow, it would be 3 steps from its starting location. The starting location of 3 is index 0 in this list here. So I would do 0 plus 3 modulus 4. And that would give me index 3, 0, 1, 2, 3, which tells me after 7 steps, the 3 will be in position 7. With the 6, it's going to be index 1 plus 3 modulus 4, which would put us at index 0. So the 6 after 3 steps is going to go to position 4, to position 7, and then back to position 3. Because of the way the modulus math is working, we can do very, very large numbers like this. And that's where that k having a max of 10 to the 9th is going to get handled. Because 10 to the 9th is a very large number, but no matter how large this number is, 3, 7, 5, 2, 6, 4, 9, or whatever, the modulus calculation of figuring out what this k is divided by the length of the list, we can always do that in constant time. Our remainder is always going to be limited to the size of the list here, which is going to be at most n cows if all the cows somehow ended up in the same group. And then it's just a matter of adding the cow's starting index, which if we can find that quickly, that'll save us a ton of time. Adding the starting index plus the remainder of the modulus math, and then doing a modulus of how many things are in the list to figure out its ending location. So in order to get these lists put together and in order to make them useful, I'm going to walk through the process of how you can build that. The official solution has one way to do it, and I have another way to do it that I think is a little easier to understand. I will explain both. The way that the, let me grab my input data again. I think it was 25, 25, and 37, 25, 37. Okay, so the way I did this, I started with my cows, actually just in an array, 1, 2, 3, 4, 5, 6, 7. And then I used a for loop to go basically to the halfway point between indexes 2 and 5. So in this case, my difference between 5 and 2 is 3. I divide that by 2 and add 1, and whatever math you need to do to figure out where your middle point is, and then just swap. So I swap the 2 and the 6, and then swap the middle point actually would have been right through the 4. Right? No, 2 through 5. No, it's not 6, 2 and the 6. It's 2 and the 5. Sorry, my line's too long there. Swap the 2 and the 5, swap the 3 and the 4. There's 2 swaps that need to take place to get to the halfway point. That would give you 1, and then 5, 4, 3, 2, and then 6, 7. So the amount of work I need to do at most is n, and I have at most m swaps. If you look at those numbers, I've got a maximum value for m of 100, and my n value is 10 to the 5th times 10 to the 5th is going to be equal to 10 to the 7th. 10 to the 7th is well within time complexity, so you are totally free to go through all of these swaps and use a for loop to manually swap the positions of the cows. Then I do 3 through 7, which is indexes 3 through 7. I do that just again as a for loop, swapping the 4 and the 7, swapping the 3 and the 6, and leaving the 2 in the middle. And that gave me 1, 5, 7, 6, 2, 3, 4. Now, in order to make this useful, the way this is laid out right now, this is telling me where the cows are. So if I say, okay, which cow is in position 2? Position 2. Then I can say that's cow 5. But that's not what I need. What I need is not which cow ended in position 2. What I need is where did the cow who started in some position end up? So if I were to look at my starting position here, if I say, okay, well, where did the cow that started in 3 end up? The cow that started in 3 ended up in index 6. But that's not immediately apparent, because if I were to look at index 3 here, that's telling me which cow is in position 3, not where cow 3 ended up. So in order to make this useful, I kind of need to invert this. Right now, what I have is I have indexes, position 1, position 2, position 3, position 4, position 5, position 6, and position 7, together with what cow is in each position. So if I were to ask, like, what cow is in position 5, position square bracket 5 would tell me that's equal to cow 2. But that's not what I want. What I want is for the cow that started in position 3, cow 3, what position did they end up in? And cow 3 ended up in position 6. So what I need is I need an array where index 3 contains a 6, rather than an array where index 6 contains a 3. That's not actually that hard to do. It's just a little bit of a mind bend to figure out why we have to invert that. But ultimately, what I need to do is I need to be able to plug in a cow and then know where they ended up. So what I can do is set up a for loop. And for every index, for I from 0 up to however many cows there are, what I then need to do is I need to have some newly created array, like maybe destination. The destination of my cow in position I is index I. So what I'm doing here is I'm saying, okay, so I've got my destination here, destination for cow 1, for cow 2, for cow 3, for cow 4, for cow 5, for cow 6, for cow 7. As I run through I, when I is equal to 1, I will go to index 1 and place a 1, using the top as my index. When I is equal to 2, I will go to index 5 and place a 2. When I is equal to 3, I will go to index 7 to place the 3. When I is equal to 4, I'll go to index 6 to place the 4. When I is 5, I'll put the 5 in index 2. I'll put the 6 in index 3. And I'll put the 7 in index 4, 7. Now what I've got is numbers that are a little different. I've got 1, 5, 6, 7, 2, 4, 3. But what this is going to let me do is now I can say, okay, so where did cow 3 go? Cow 3 ends up in 6. So where did cow 6 go? Cow 6 ends up in 4. Where did cow 4 go? Cow 4 ends up in 7. And then where did cow 7 go? Oops, that's a 7. Cow 7 ends up in 3. And then that's a loop. So that was the way that I constructed my destination array. The official solution gives another approach. I found this one a little harder to understand, and it wasn't the first one I came up with, but I will demonstrate it because it's a good technique to know, and it may come up more useful in other problems. So what they did, and this runs in the same time complexity as far as I can tell, is they said, okay, I'm going to treat this like I want to jump straight to this end result, which means that I'm treating these initially like these are the destinations for each cow in each of these positions. With 0 swaps, cow 1 would be in 1, cow 2 would be in 2, cow 3 would be in 3. In order to figure out where all these cows are going to be after a swap from 2 through 5, what we're looking to do is say, okay, if cows 2 through cows 5 were to change their direction, then what that means is that however far we go from the left side, that's how far the cow must be from the right side. But I'm not going to directly swap cows 2 and 5. I'm only going to update their positions. Now, on the first step here, that actually is going to do the same thing, whichever step you'll use. But basically what we're looking for is we're saying, okay, for some cow in position X or whatever position is, for a cow in position X, the location that it's going to end up in after the swap is going to be its distance from the left side, which would be px minus 2, for example, in the 2 through 5 swap. And then it's going to be that many steps from the right side, which would be 5 minus px minus 2, where 5 is your right number and 2 is your left number. If we distribute that minus sign, what we're left with is 5, which is the right, plus 2, which is the left, minus px. And for any given position, that's going to be the position where they will end up in after the swap. So looking at how that's going to run here, I have to go through every single cow because, again, these are the ending positions of every cow, but I don't necessarily know what index I need to check. On the first one, all the cows are in their starting indexes, but this will make more sense when we do the 3 to 7, why we have to go through all of them. So for any cow that is in the range of 2 to 5 in its current position, remember these represent positions, not the cows in a position, but the positions of a cow. So again, your index is your cow number and the value is the position rather than the other way around. Before we had the cows be here and the positions was the index. So position 4 was cow 4. Now we're doing it backwards. Cow 4 is in position 4. So anything that's between 2 and 5 inclusive is going to be fed into this formula down here, 5 plus 2 minus p of x. So 1 is not in that range, so 1 is going to stay right where it is. 2 is in that range, so I'll have 7 minus 5, 6, 7 minus 2, which is going to be 5. And that's true, that cow does end up in position 5. 3 is going to be 7 minus 3, which is going to be 4. This is going to be 3, this is going to be 2, and these will stay 6 and 7. Now again, it's not totally clear why this is different yet because the cows were all in their starting positions at the very beginning. But what's going to happen here is when we do this again with 3 to 7, we're going to have a slightly different result than we did when we just swapped them. Because before, when we did 3 to 7, we ended up with 7, 6, 2, 3, 4. This time, what's going to happen is we're going to go through all the cows, looking only for cows that are currently in positions 3 through 7, and we're going to feed them through this same formula we have before. Now, this is going to be 7 and 3 instead of 5 and 2, which is 10. So every cow's new position based on its current position is going to be 10 minus its current position. So before, we only focused on indexes 3 through 7. But this time, and again, this is just an alternate version to do what we already did. We're going to look at every single cow, current position, and feed it into this formula. So cow 1 is still in position 1. This cow is in position 5. Cow 2 is in position 5. This doesn't mean cow 5 is in position 2. This means cow 2 is currently in position 5. Position 5 is in the range of 3 to 7, so we have to feed it into this formula, which is going to be 10 minus 5, which means this cow is going to come up with 5. So it was in position 5, and it will remain in position 5. And if you remember back, the cow 5 did end up in position 2. Cow 2 did end up in position 5. So cow 2 was affected by the first swap, and the 5 would have been placed into index 2. Cow 5 would have been here. Now this next swap won't affect the cow that was placed there, which is why this one's not moving. Let's run through the rest of these. Cow 4 is 10 minus 4, which means cow 3 was in position 4 and now is in position 6. Cow 4 was in position 3, which is in that range, which means now is in position 7. Cow 2 is not in that range, or cow 5 is not in that range. Cow 5 ended up in position 2. That's what this 2, remember, this is the position of cow 5. Index 5 is cow 5. Position 2, since cow 5 is currently in position 2, which is not in the range of 3 to 7, cow 5 will not change position according to this swap and will remain in position 2. Cow 6 is currently in position 6. It will be affected by this. So we'll do 10 minus 6, which is 4, which means cow 6 will end in position 4. Cow 7 is currently in position 7, will be affected by this swap, and will end up in position 3. Now, this actually is what we did right here earlier with that swap. And you may want to watch those two twice, because again, this is 2 different ways to get the same thing. What this second method is doing is keeping track of the position of every cow rather than the cow in every position. By doing it this way, we don't have to invert it at the end, but we do get the same solution. So whichever one of those ways you're more comfortable with, again, my 2 cents is this method here, I feel is a little confusing, but this is showing, for example, cow 2 is in position 5, since that would affect, if I have 1, 2, 3, 4, 5, 6, 7, if I have 7 cows and cow 2 is in position 5 and I'm doing a 3 through 7 swap, 3, 4, 5, 6, 7, then you can see that the distance from the left and the distance from the right are identical. And that's why that cow didn't move, because the distance from the left would have been index 5 minus index 3, which is 2 steps from the left. And then we would get index 7 minus 2, which gives us 5. And then it shows that it actually starts and ends in index 5. Or again, you can just use the method that I was demonstrating in the beginning, which is to write all the cows 1, 2, 3, 4, 5, 6, 7. Swap 2 through 5, 1, 5, 4, 3, 2, 6, 7. Swap 3 through 7. Again, you can do that in a for loop. 1, 5, 7, 6, 2, 3, 4. And then run through with a for loop and just make sure you invert this so that instead of having the cow in each position, we have the position for every cow. Okay, so let's back up to those golden numbers we generated a minute ago. So I had 1, 5. Actually, let's go ahead and just keep solving forward from here. It doesn't hurt to do that one more time. Okay, so what this shows me then is the position of every cow. Cow 1 ends up in position 1. Cow 2 is going to go to position 5. Cow 3 is going to go to position 6. Cow 4 is going to go to position 7. Cow 5 is going to go to position 2. Cow 6 is going to go to position 4. And cow 7 is going to go to position 3. So once I've generated this, now what I need to do is I need to generate those groups. And I kind of briefly mentioned that before. We need to set up those groups. So starting from group 1, what I'm going to do is I'm going to keep track of, for each of these 7 cows, what is their group? 2, 3, 4, 5, 6, 7. And what is their order within that group? Order 1, 2, 3, 4, 5, 6, 7. Okay, so running through these steps, I can see that cow 1 is going to be in group 1 because I'm starting with group 1. So I'll put cow 1 in group 1. Group 1 is going to start with cow 1. I then am going to essentially have a while loop where I'm going to run through until I do a full cycle. So cow 1 just goes straight to 1. That's already a full cycle, which means the index in group 1 of cow 1 is index 0. Cow 1 is the first thing in the order of cows that are in group 1. So if I go to first index here, if I go to first index here, and here now I'm 0 indexing just to make it more confusing. But we've been 1 indexing up until now. I'm just going to 0 index the groups just to make life easy. Group number 2 begins from cow 2. Cow 2 is going to go to group 2. And then group 2 is going to start with cow 2, which means cow 2 will be the first thing in group 2. So again, if I go to index 2 for the group, I can see cow 2 is in group 2. If I want to know the order, I can see cow 2 is in position 0, which we're just going to say that's the first position in group 2. Now my while loop begins. I get to cow 5. Cow 5 is also in group 2. So 2, 3, 4, 5, also group 2, 3, 4, 5. But cow 5 is the second item in group 2. So I'm going to put a 1 here to indicate cow 5 in position index 1. From 5, we're going to go back to 2. 2 is where we started. So that means that I don't need to go any further with group 2. Group 2 is done. And that's handled cows 2 now, and actually cow 5 already got placed. Now, what we don't want to do is we don't want to do this sequence for every single cow. The reason why we didn't do this for every cow is if I had to do, let's look at 3, 4. Let's look at a simpler version. If I had cows 3, 4, 5, and 6, if I wanted to brute force this, then I would say, okay, cow 3 goes to 6, then from 6 goes to 4, then from 4 goes to 7. Cow 4 goes to 7, from 7 goes to 3, from 3 goes to 6. Cow 6 goes to 4, from 4 goes to, you can see I'm repeating this process. So the reason why we're doing these as groups and not just have each individual cow run through its sequence of steps is because if I have n cows that I have to potentially run through n steps, I'm in n squared time. What I need to do, and the reason I'm building these groups, which I think I've kind of skimmed that a little bit, but the reason I'm doing these groups is because I don't want to figure out that cow 3 goes to 6, 4, and 7, and then that cow 6 goes to 4, 7, and 3, and then that cow 4 goes to 7, 3, and 6, because that's a repeated calculation, and I don't want to repeat those calculations. So I can't do this on a per cow basis. It would not be in time complexity for me to go through each cow and then calculate where they end up. What I need to do is figure out their groups so that then I can do each group one time. And even though I'm going through all of my cows here, when I place them in a group, I later won't be doing any calculations on that cow. And you're going to see that with group 3. And that's why I'm pointing that out again right now. So cow 3 is going to be in group 3, which puts them in the 0 position of group 3. From there, it goes to cow 6, or position 6. Position 6 is also going to be a cow. Let me get my cow 3 in here. So from 3 goes to 6, which means cow number 6 is also in group 3, and is the index 1 is the second item in group 3, 6 and 7. From 6, we'll go to 4, which means cow 4 is also in group 3, and cow 4 is in 4 in index 2 of that group. From 4, we go to 7. So cow 7 also is in group 3, and is going to be in index 3 of that group. I kind of ran out of room there. 3. Okay. So what I've got now is I've got my groups and I've got my ordering. I can see that cow 1 is the only thing in the group. Cow 2 is in a group, or group 2 has cows 2 and 5. Cow 3 is in a group with cows 6, 4, and 7. Having now done this, whatever my K value is, I can tell immediately for each cow where they start in the group and what their order is. So let's say, like, for example, my K was, let's do K equals 7. So I want to know where is cow 1, 2, 3, 4, 5, 6, and 7 after doing 7 operations. Let's start with 1 operation and then do 7. I think that'll be a little easier to see what's going on. So we'll start with K equals 1 and we'll go from there. So K equals 1 means we're going to do all these swaps one time. Cow 1, if I go to index 1, I can see cow 1 is in group 1, and the position currently is in index 0. So cow 1 is in group 1 in index 0. I have this table here, which I'm going to have to build. This probably, you can use a vector of vectors for this, or you could use, I guess, a map of vectors, or whatever makes sense for the language you're using. I would go to group number 1, which I looked up cow 1 is in group 1. I would get the index of the starting position 0 plus K, which in this case is 1, modulus the length of this list, which is also 1. Which 1's going to start and end in the same position no matter what those numbers are, so it's not that exciting. I want to know with K equals 1, where did 2 end up? So I look at group 2. Group 2, or cow number 2 is in group 2. The starting index for cow 2 is index 0. So once again, 0 plus K, which is 1, modulus 2. Because 2 is how many things are in this group. So that's how many steps forward we're going to go. That's going to give me 1 step forward. Actually, I'm doing the modulus on the wrong side. These parentheses should be starting position plus steps, final result modulus 2. Okay, so 1 modulus 2 is going to be 1. Index 1 of this list is 5. Tells me cow 2 would end up in index 5. We'll just do up to cow 3 and then I'll change the K value, because then the rest of it's going to be the same kind of thing. For cow 3, I'll see that cow 3 is in group 3. Well, I'll do cow 3 and cow 5, or cow 3 and cow 4 rather. So cow 3 is in group 3. Cow 3 starts in index 0 of group 3. My K value is 1. So I'm going to have 0 plus 1 modulus 4 in this case, because there's 4 members of that group, which is still just going to be 1. So that's 6. That shows me that 3 is going to end in position 6. And then cow 4. Cow 4 also was in group 3. We'll do cow 4 at least. Cow 4 was in position index 2 of group 3. So index 2 of group 3 is this right here, and that is in fact where that cow is. My starting index 2 plus my K value of 1. Final result, modulus 4 gives me 3, which tells me that cow is going to end up in index 7. And we can see just looking at this, this is where they go after one swap. 4 goes to 7, 3 goes to 6, and so forth. With a K equals 1, it's only one step. So let's try a different K value. We're going to do K equals 7. That'll be a little bit more interesting. K equals 7. Let me clean these up a little bit. Okay. All right. So with a K equals 7, we want to know where all these cows are going to end up. So cow number 1. Cow 1 is in group 1 in position 0 of group 1. Position 0 of group 1 plus 7 steps modulus the size of the group. Size of the group is 1 item. Anything modulus 1 is going to be 0, which means cow 1 ends up in index 0 of group 1, which is position 1. Cow 1 is not going to change place no matter what. Cow 2 is in group 2 in position 0 of group 2, which means the same formula is going to happen. We're going to be 0 plus 7, but this time modulus 2, because there are 2 members of group 2. So after 7 steps, the starting position of 0 plus 7 will be 7. Modulus 2 will be 1, which means the ending position of cow 2 will be index 1 of its group, which is position 5. Then on to cow number 3. Cow 3 is in group 3 in index 0 of group 3. So that's here. 0 plus 7, but this time modulus is going to be, let me move this over here a little bit. 0 plus 7 modulus 4. I think I'm over my video here. Okay, so starting position of 3 is index 0 of group 3. I'm going to do plus 7, which is going to give me 10. Modulus 4 is going to be 2, which is going to mean that index 2, 0, 1, 2, this is where cow 3 is going to end up after 7 steps. 1, 2, 3, 4, 5, 6. Hang on, that's not right. Let me double check that. Index 0 plus 7, 1, 2, 3, 4, 5, 6, 7. So modulus 4 is 3. Yeah, that's right. That's right. That's right. Okay. So yeah, if I go 7 steps, then 3 is going to go 1, 2, 3, 4, 5, 6, 7. It should be 7. I'm just double checking my sanity here. And then 0 plus 7 modulus 4 would be remainder 3, which would be index 3 of this group. And then 3 would in fact end up in index 7. That's where 3 would go after 7 steps. Wherever 3 goes after 7 steps is the same as where it goes after 3 steps, which is to position 7. Cow in index 4. 4 is also in group 3, starting in index 2. So we'll have 2 plus 7 modulus 4, which is 9 modulus 4, which is 1, which means that's going to be index 1, which is position 6. After 7 steps, cow 4 will end up in position 6. We have cow 5. Cow 5 is in group 2. So we'll do, that changes this formula. Cow 5's starting position in group 2 is position 1. It is in index 1 of group 2, plus the 7 steps, and then modulus 2 is going to be index 0. That shows that the 5 will end up here in index 0, which is position 2. Moving on to the next cow. Cow 6 is in group 3 in index 1 of group 3. So we'll take that starting index 1 plus 7, and then group 3 has a member size of 4. So this will be index 0. That'll show that the cow 6, which is in index 1 of group 3, will do 1 plus 7. Modulus 4, which is 0, will end in index 0. Cow 6 will be in index 3 at the end. Final cow is cow 7. Cow 7 is in group 3 in index 3 of group 3, which is right here. So I'll take my starting index of 3. I'll add the 7 to get to 10. Modulus 4 is 2. Index 2 is 4, which will tell me that 7 will end in position 4. So basically, that's the process. And I know this is a lot of steps. This is probably one of my longer videos. But what we're essentially doing, kind of just glance back at this. We start by writing out our cows in an array, 1, 2, 3, 4, 5, 6, 7. Manually do these swaps, swap, 1, 5, 4, 3, 2, 6, 7, and then 1, 5, 7, 6, 2, 3, 4. Invert this so that your cow position gives you its index rather than the position giving you the cow gives you the position. So we'll know that 1 goes to position 1, cow 2 goes to position 5, cow 3 goes to position 6, position 6, and so forth. Once you have that, you break them off and figure out what their groups are going to be. We need to get the group number of each cow and its position, its index within that group. So group 1, group 2, group 3, group 1 having only 1, group 2 having 2 and 5, filling that in as we go. So group 1, position 0, cow 2 is in 2, position 0, cow 5 was in position, or cow 5 was in group 2, position 1, cow 3 was in group 3, position 0, cow 6 was in group 3, position 1, and so on and so forth. Once we get that, then we have our groups and our positions. Then we loop through for every cow. For every cow, we look up its group, we look up its index within that group. We add that to whatever our K value is. We do modulus, whatever the size of the group is. And then we take the index, whatever index that gives us tells us its ending index. And then that's going to be where it's going to be after that many steps. So that's the algorithm. Good luck coding it. And I will talk to you on the next